we already talked about how to make an ionic formula from Lewis structures. And the thing that we need to do next is really talk about how to do that a little bit quicker, because it took a while to draw Lewis structures for all the magnesium and phosphide ions in magnesium phosphide. We looked at the fact that we had, each magnesium losing 2, each phosphorus gaining 3, and so we ended up with a formula of Mg3P2. But there's got to be a lot quicker way to do it, and there is. Okay, the reason we showed you this way is because this is what's really happening, and this is why we end up with the formula, Mg3P2 as the final formula for magnesium phosphide. But a shortcut is to use something called the least common multiple, which you've probably, might remember from math class. So, but before we get into actually using least common multiple, we're going to need to know the charges of our ions. And a quick way to know what the charges are by looking at the periodic table is by looking at what group the element is in. So, of course, we know that the noble gases over here in group 18 are not going to have a charge because those guys are already stable. So I'm just going to put a 0 above that number, or above that group, pardon me, because that doesn't form ions. But if we think about it, everything in group 17 is going to form an ion that has a charge of -1. And the reason for that is because everything in group 17 is just 1 electron away from being like a noble gas. So, for example, fluorine is just 1 electron away from being like neon, chlorine is 1 electron away from being like argon, and so forth. So they're all going to form -1 ions. I know that without even drawing the Lewis structures, just by where they are and how many spaces they are away from the noble gases. Everything in group 16 is 2 electrons away, so everything in group 16 is going to form a charge of -2. Again, I know that without even drawing the Lewis structure because it's 2 spots away from the, oxygen is 2 spots away from neon on the periodic table, sulfur is 2 spots away from argon, etc. And then everything in group 15 is going to be -3, okay? So if we look at the other side of the periodic table, we're going to have the opposite happening. Everything in group 1 is going to be +1. And you should probably mark this on your paper periodic table, or just kind of make a mental note as you're working. It's probably easier, at least at first, to have it marked on your periodic table. And everything in group 2 is going to have a charge of +2. And that is because everything in group 2 has 2 valence electrons, and so everything in group 2 will lose 2 valence electrons to become like a noble gas. Skipping over the D block to the P block, boron, aluminum, gallium, indium, those guys are all going to be +3, okay? That's because they have 3 valence electrons, so they're going to always lose. Now, I'm not going to put anything above group 14, and that's because these top 2 guys, carbon and silicon, don't even tend to form ions very often because they're so small they tend to share electrons. And these guys down at the bottom, germanium and tin and lead, if we were to go down a bit further, those tend to give up electrons, but we'll talk about them a little bit later on. For right now, I just want you to be able to predict the charge of an ion based on what group it's in. So if I were to ask you, what charge would you expect sulfide to have, you could say to me, well, sulfur is in group 16, and everything in group 16 has a -2 charge when it forms ions. So you would say S is going to have a 2- charge, even without having to draw the Lewis structure. So that's just the charge of the ion. Everything in group, 13 is going to be +3. So if I said, what's the charge going to be on aluminum, just by its position on the periodic table that it's going to be +3. Okay, so how do we use this using least common multiple? Now, so least common multiple, if you remember from math class, if you just list the multiples of numbers. Let's say, for example, we're talking about the number 2, its multiples would be 0, 2, 4, 6, 8, etc. So these would be multiples of 2. In other words, 2 times 0 is 0, 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6, etc. If I do the same thing with 3, I get 0, 3, 6, 9, 12. So I'm just counting by threes. in least common multiple means I'm basically just searching out the smallest number that these two numbers have in common. So if I want to know the least common multiple between 2 and 3, that's going to be 6. Okay? Now, how does this come in handy when writing a formula for an ionic compound? Well, if I have a formula like, let's say, magnesium phosphide, magnesium it was magnesium phosphide, sorry. Magnesium phosphide, I already know what the answer is supposed to be, Mg3P2, but how would I find this a little bit quicker than drawing out all those Lewis structures? Here's what I do. I go to my periodic table, I look at the charges. Magnesium's in group 2, so I expect it to be +2. Phosphorus, which forms phosphide, is in group 15, and everything in group 15 is going to be -3, or 3-. And what I do is I just look at the least common multiple of the two numbers. And don't worry about the negative and positive signs, just focus on the number itself. So we just said the least common multiple of 2 and 3 would be 6, right? So what you're going to do is you're going to try to make the positive charge add up to +6 and the negative charge add up to -6 so that they cancel out, because these compounds are going to have 0 overall charge in the end. And so what number would I have to multiply my +2 charge by to get +6? Okay, so you should have said 3, right? Because 3 times 2 is +6. And then what number over here, what subscript would I put here so that my -3 times that number gives me -6? Right, so you should say 2. So in other words, -3 times 2 gives me -6. It's always important that my total positive charge, in this case 6, cancels my total negative charge. So -6. So I end up with a formula, if I just rewrite this, of Mg3P2. Okay, using the least common multiple of 6. Now, why does that work? What does it have to do with our Lewis structures? Well, if I look at my little X's that I drew, I have 1, 2, 3, 4, 5, 6 X's. So 6 total electrons were transferred from my 3 magnesiums to my phosphorus atoms. So some of them were coming from multiple places, but these 3 magnesiums gave up a total of 6 electrons to make this compound stable. Or you could say the phosphorus gained a total of 6 electrons between the two ions. So 6 electrons were exchanged. All right, and the reason that our total charge has to always add up to 0 is because the number of electrons have to, the electrons are transferred, which means they're not being gained or lost. They're not just disappearing or appearing. If magnesium loses an electron or 2, that same number of electrons has to be gained by the negative ion. So that's why our charge has to add up to 0. And of course, +6 and -6 adds up to 0. So let's try it with another one. Let's try, let's see if this works with gallium nitride. Okay, so look at the periodic table, come up with the charges for both ions. So you should have said 3+ and 3-, right? So this one is unique because the least common multiple of 3 and 3 would just be 3. And so what that means is the gallium already has a +3 charge just with one ion, and the nitrogen, or nitride, I should say, already has a -3 charge, so they already cancel out. So because the magnitudes of these two charges were equal, we end up with a 1-to-1 ratio. So we get the formula GAN for gallium nitride.